Welcome again. Welcome to the Electronic Circuit Lab. Today we would be perform the second practical on the subject Electronic Circuit Lab. So the aim of the second practical is to build, simulate or test a single stage common source configured N-channel MOSFET amplifier with source bypass capacitor. The objective of this practical is first to simulate and analyze single stage common source eMOSFET amplifier with source bypass capacitor to find the input impedance, output impedance, gain and frequency response. Second objective is to understand the effect of bypass and shunt capacitors on gain and bandwidth. The outcome of this practical is the learner will be able to simulate using modern simulation tools to analyze the performance of eMOSFET amplifier. Second outcome is to know and can design the circuit components affecting the frequency response of an amplifier. How to control the bandwidth of an amplifier as per the need of the application. If you would be going to map the outcome of the experiment with the course outcome given by the SPPU, so it would be mapped with the two course outcomes. First, assimilate the physics, characteristics and parameters of MOSFET towards its application as an amplifier. Second, design MOSFET amplifier with and without feedback and MOSFET oscillators for the given specification. So these two course outcome would be mapped with the experiment outcome. Now we have to see the list of or the software required for this experiment is multi-sim or any other simulation teams. There are the various simulation tools are available for simulation of the electronic circuits. You can use any one of them. What are the components basically we are going to use for this practical? These are the resistors that is mentioned here in the table: RD 2.2K, RS 1K, RG1 20 mega ohm, RG2 10 mega ohm, RSG that is the resistor of the voltage source that should be greater than the RI, and 8 mega ohm I have taken because RI is coming nearly 6.67 mega ohm, and RL the load resistor that is less than the RO, that means it would be a 1K. If you are going to see the coupling capacitors value are, so the coupling capacitor values would be 10 microfarad input and output coupling capacitor, bypass capacitor would be 100 microfarad, and shunt capacitor would be 22 nanofarad. So where it would be required, we would be see when the experiment progressed. And all the value of the resistor has been taken from the experiment number 1, because the same circuit we have taken in the experiment number 1 for the DC analysis, and this is now we are going to perform the AC analysis. So if you have to see the circuit diagram, this would be a circuit diagram for the common source amplifier using the voltage divider bias and using N-channel enhancement type MOSFET. So here we are using the N-channel enhancement type MOSFET is there. If you have to see the circuit diagram, it is very much similar to the first experiment of the DC analysis. All the resistor value are the same. Only we have added the AC component like coupling, input coupling capacitor, output coupling capacitor, then bypass capacitor, as well as we have also added the source resistor, load resistor, shunt capacitor as per studying of the frequency response of the amplifier, as well as we have to also provide the AC voltage source as a function generator, and we would be observe the output in the CRO or DSO. Okay, so this much of the requirement is there. This is the circuit diagram I have shown as we would be going to construct in the multi. So in this diagram you can easily observe the function generator is there. See the function generator and the CRO as a observing device. And the rest of the circuit would be as similar to the first segment, only the coupling capacitors has been be added because we are going to perform the AC signal analysis. So a function generator would be generate the AC input signal. For that we have to require a coupling capacitor to couple the AC signal to the input of the amplifier. Now just little bit see the theory of this practical is. So amplification is a process of adding strength in terms of voltage or current or power to the signal of interest. It can be measured by observing the increase in amplitude level of the input signal on the output side without change in the frequency and the phase characteristic of the input signal. So basically we are going to perform the common source amplifier. So we know that the phase shift is 180 degree with respect to the input signal. And whatever our operating frequency, that would be not changed for the output signal. It is same as we have using the as input signal. The amplification basically depends upon the input and output impedance offered by the transistor. If you have to be see the coupling capacitors, CC1 as input coupling capacitor and output coupling capacitor CC0 is used to couple the maximum AC signal and blocking the DCC, and this capacitor decides the lower frequency cutoff, that is FL cutoff. Similarly, the another capacitor is used here, that is bypass capacitor, passes the AC and blocks the DC. It improves the gain of the amplifier. The main role of the bypass capacitor is to improve the gain of the common source FET amplifier by reducing or eliminating the voltage drop across the source resistor, or you can say it is by eliminating the AC negative feedback. And this capacitor dominates the low frequency cutoff, usually FL. So FL cutoff would be depend upon the coupling capacitor, input coupling capacitor and output coupling capacitor, as well as the bypass capacitor, but mostly it would be depend upon the bypass capacitor. Now we have to come to the other end of the bandwidth, that is upper cutoff frequency of an amplifier, that could be decided by the inter-electrode or internal or parasitic capacitor, that is CGD, CDS, CGS. Okay, with the wiring capacitance. The CGD provides a dominating effect. CGD means capacitance developed between the gate and drain terminal on the higher frequency cutoff in the common source inverting amplifier, which can be modeled using the Miller's capacitance that we have already learned in the theory about the Miller effect. The upper frequency cutoff can be manipulated using the external shunt capacitance to design the desirable bandwidth of the amplifier. Now we have to come to the practical side of this voltage amplifier. The input impedance should be as large as possible, and ideally its value is infinite. The output impedance should be as small as possible, ideally should be 0, and the voltage gain should be as large as possible, ideally infinite. So from this statement we can know the ideal value of the input impedance and output impedance and the voltage gain, and the practically what should be the value of these parameters. Now we have to see the procedure how to perform this practical. So to found the AC performance parameters, what we have to do, we have to first define the Sinusoidal value of the sinusoidal AC input test signal. The frequency we would be take here as a 2 kilohertz. That is 1/10 of the maximum frequency of the audio amplifier. The maximum frequency of the audio amplifier is 20 kilohertz. So 1/3 of that value would be taken. And this signal frequency would be generated by with the help of the instrument that is called the function generator, and connect it to the amplifier without RSG and RL, and observe the 180-degree phase shift between the input and output signal. Second step is, now we would be measure maximum undistorted output signal, that is the V0, without RSG means signal generator resistance, without RL means the load resistance, by adjusting the voltage amplitude level of input signal 2 kilohertz, and also note down the maximum input voltage signal. So here we are actually studying the small signal amplifier. So we would be limit the maximum value of the input voltage signal up to 13 millivolts. Practically, you can take it maximum 100 millivolt. Third step is, after this we have this maximum input voltage signal level, the frequency are kept to be constant and rest of the measurement of the output voltage. Measure the output voltage V0 dash with RSG and without RL. Find the input resistance. So when we have to be connect the RSG in series with the input coupling capacitor and do not connect the RL, so at that time your voltage signal would be decreased from the previous value of V0, and the new value is defined as the V0 dash. And this V0 dash would be useful to finding out the input resistance Ri. The formula for input resistance Ri is V0 dash upon V0 minus V0 dash into RSG, where V0 is your maximum undistorted output voltage without RSG, and without RL, V0 dash is the maximum undistorted output voltage with RSG and without RL. In a similar fashion, we would be calculating the output resistance also. So for this, measure the output voltage V0 double dash without RSG but with RL. The formula for finding out the R0 is V0 minus V0 double dash upon V0 double dash into RL. Here V0 double dash is what? Maximum undistorted output voltage without RSG and with RL. So this is the practical procedure for calculating the input resistance and output resistance. So remember these two formulas and the methodology. Now the next step is measure the output voltage with RSG and with RL also. So in this way we have to be going to define 4 parameters. 4 parameters are there. So which are these 4 parameters we have to be going to see? AV, that is equal to V0 upon Vi, that is the undistorted voltage gain. Then there is a AVS, where we have to be connect the RSG V0 dash upon Vi. Then AVL, when we have to be connect the load resistor and without RSG, that is V0 double dash upon Vi. And finally VSL, that is with connecting the RSG and RL, that is V0 triple dash upon Vi. So with the help of these calculations, it would be useful for finding the actual undistorted gain, input impedance, output impedance, and the bandwidth of the amplifier. At the final step is simulate to find the lower and upper cutoff frequency of the amplifier using the AC analysis for the following conditions. We have to be observe the effect of bypass capacitor and source resistor. Keep input coupling voltage, coupling capacitor 10 microfarad and output coupling capacitor 10 microfarad as a constant level, and measure the lower and upper cutoff frequency for bypass capacitor equal to the 22 microfarad. Now we would be vary the value of the bypass capacitor from 22 microfarad to the 100 microfarad. So there is a 2 value of the bypass capacitor, because we know that CS is the dominating capacitance to decide the value of lower cutoff frequency. Now, in the similar fashion, to observe the upper cutoff frequency, here we can't show the internal junction capacitances, so we would be use a shunt capacitor to observe the value of the upper cutoff frequency. And for this purpose, we have to be connect a shunt capacitor parallel to the amplifier at the output section, and keeping the input coupling capacitor and output coupling capacitor bypass capacitor to the actual value of 10 microfarad and the 100 microfarad respectively, and measure the lower and upper cutoff frequency of the amplifier. For shunt capacitor, that would be equal to the 25 nanofarad or maybe 22 nanofarad you can take. It depends upon the availability of the capacitor. And compare the result of without shunt capacitor and with shunt capacitor. Okay. Now, before going to the calculation, we would be first see the simulation. If you are going to see the simulation, again we are going to share the multi-sim here. So for the sake of simplicity, I have already drawn the circuit diagram to save our time. We have already seen the procedure of drawing this diagram in the first experiment, so I am not going to repeat it. So as per our circuit diagram, we have connected all the resistors R1, R2, R3, R4, VDD, and the coupling capacitor 10 microfarad, output coupling capacitor 10 microfarad, bypass capacitor 22 microfarad, and 100 microfarad. Both would be calculate. Okay, so keep it as first case, the original condition 100 microfarad, change the value bypass. And the other component that we have to record RSG and RL and shunt capacitor, we have to be keep it as per our requirement. Now see what amount of input voltage we have to be required to apply. You have to be see double click on this function generator. So we have to apply the signal frequency of 2 kilohertz, 1/10 of the audio amplifier maximum frequency value, and amplitude would be keep in the 50 millivolt peak value, and if you have to see the peak to peak, it is 100 millivolt. Okay, double of this peak amplitude. Now take the sinusoidal. There is a triangular and square wave is also available. We have to take a sinusoidal signal, and we have to be, there is a 2-channel oscilloscope we are going to use here. So channel A is used here to observe the output. Channel B is used here to observe the input signal. That's why we have to connect a wire to the input, means function generator signal. Keep the positive polarity of the function generator to the input of the amplifier, and common is connected to the ground. Negative terminal would be not used. One more thing we have to be take care of, that change the color of this input wire so that it would be easily differentiate between the input and output signal that would be displayed on the CRO. Now there is a simulation button is there, switch. We have to just turn on this switch. Before that we have to double click this CRO. Okay, and if you want to better observation, you can little bit shift this circuitry so that all this component would be easily observable. Okay. Now you can simulate this. When you have to simulate, and just pause this simulation, change the background color here. Okay. Now this red color is connected to your channel A, means this is the output, and the blue color is connected to the input of the amplifier, means blue color indicates the channel B, that would be indicating a input signal, and the red color is indicating here the output signal. Okay. Now first of all we have to be, there is a 2 scales are there to measurement of this, the level of input and output signals. So first of all we have to be adjust the scaling of the time base. So we have applied the signal of the 2 kilohertz. So when we have to be converted into the time period, it will become 500 microsecond per division. Okay, and little bit we will expand this to 200 microsecond per division. We have to be keep to observe the waveform clearly. In a similar fashion, if you have to be see here, so at the same time, this channel would be we have applied the 50 millivolts, so we have to be keep the scale in the 50 millivolt per division, and this would be amplified channel A, that will be the some higher value of the voltage, maybe 1 volt here. Keep the signal on the AC positions. Now see the we have to be keep this scale 1 on the negative peak of the input signal and positive peak of the output signal. That would become nearly 99.9, means 100 millivolt you can take as the input signal, peak to peak value, and output would be also observed in the red signal, that is also peak to peak. And we have to be know that the phase difference between input and output is 180 degree. That's why the output signal would become as a negative, and it is coming nearly the 3.38 nearby. Okay, so this is the signal that we are going to calculate it here. Okay, now you can put up this value on your observation table. We would be later on show you that uh, all the values at a once. Now this is the first. This is called the V naught. After calculating this V naught, that is nearly coming to 3.4 volt. So you can observe that it would be coming the nearly the 34 times the gain is very high. Now we have to be observe the V naught dash. So how we have to be calculate this V naught dash? For calculation of this V naught dash, what we have to be do? Turn off the simulation and connect a RSG. So RSG should be greater than this input impedance. The input impedance would be the parallel combination of 20 and 10 mega ohm, nearly the 6.67 mega ohm is there. So it would be take someone greater than this value. And now RSG here is calculated in series with the CC1 or coupling input coupling capacitor. And now you would be observe the output value after simulation. You would be see a very drastic change in the value of the output signal. So it would be easily now the output voltage drops significantly. If you have to be see, it would be drop very much significantly, and keep observing the output value. It would become nearly 34.5, okay, millivolt. Then you can see that the voltage gain is dropped, and it is nearly less than that of the input voltage. This is the effect of this, because the RSI is very large here and it is greater than this, so it would be giving a it would be responsible for providing a loading effect, and because of this loading effect, what happens, your output signal would be decreased in magnitude. Now we would be observe this is the V naught dash. Now we would be observe the V naught double dash, and the condition for V naught double dash is disconnect this RSI or RSG, we can say here, and connect a load resistor across the transistor, and the one end of the load resistor is connected to the ground. You can connect here also like this. Now simulate it again, your signal would be increased. Change the color of this. Okay, now observe the output, and you would be see that now your output is more than this V naught dash. Okay, and you can observe the value of this output. You can easily see this value would be nearly the 1 volt. Okay, it is much larger than the V naught dash, but less than the V naught. So V naught is the here the maximum value of the output voltage, undistorted maximum output voltage. So this would be also used for the calculation of the R naught. In a similar fashion, you can also connect both the resistor and calculate the V naught triple dash also. That is also mentioned in our calculation. So again, your input voltage is decreases significantly, and you can measure this value. I have already measured, but for the sake of practical, I am showing you how to measure 31.2 millivolt. So these all are 4 voltages that we have to be required to calculate, because it would be helpful for finding out the voltage gain, input resistance, and output resistance. Now we have to see the observation table. Now here again we have to be back into the observation table. So you have to find out that AC performance parameters for applied 2 kilohertz and 100 millivolt. Actually this is 100 millivolt peak to peak. Okay, and 180-degree out of phase shift is there. So the output voltage is coming undisturbed without RSC and RL, that is 3.44 volt nearly. V naught dash is 30.45 millivolt, and V naught double dash is 1 volt nearly, and V naught triple dash is 31.44 millivolt nearby. So where this value would be used? This value would be used for finding out the value of the voltage gain. Okay, so if you have to we have to calculate AB is equal to V naught upon VI, 34.4 ABS, that is 0.34 AVL, 10 AVSL, that is 0.31 RI V naught dash upon V naught minus V naught dash into RSG, that is 891.7 kilo ohm. R naught, that is again V naught minus V naught double dash upon V naught double dash into RL, that is 2.44 kilo. So in this way we have calculated all these parameters: input resistance, output resistance, and voltage gain. Okay, now we have to see the frequency response and calculating the FL and FH. So see how we have to calculate this. For observing the value of the frequency response, first of all we have to know the value of the output node, that is mentioned in net name 5. So we would do the AC analysis now. So what is the procedure for doing the AC analysis? There is a grapher like structure is there. You have to click on this, click on the AC analysis. Frequency parameter you have to be set 1 Hz, 10 gigahertz. Decade, number of points per decade is 1000. There is a various types of the vertical scale. You have to select the decibel. Select the output. Output we know that we have to voltage we have to select the V5. So already we have selected. You can again, I am showing how to select it. Click on the V5, add it. Okay, and other things as it is. Simulate this. Okay. There is some problem. The problem is we have already connected this RL. We do not need to connect. First of all, we have to observe the V naught and calculate the voltage gain on basis of this. Okay, sorry. Now again do the same procedure, and when you have to repeat this procedure, you will get the. This is the way that we have to calculate the value of the observe the frequency response. So if we have to see the frequency response here, so we have to also select the scales. Scales are chosen by this. Okay. Now how to use these scales? If you have to see, So first of all, we have to observe the frequency response. Bring both the scales on the maximum value of this your curve. This is AB, voltage gain in decibel versus frequency in logarithmic scale. Semi-log scale is there. So x1 is representing the frequency of scale 1, y1 is representing the voltage gain, x2 is representing the frequency again for scale 2, y2 is representing the voltage gain, y2. So the maximum value we have to be calculated 4.78 nearly. So we know that FL is 3 dB less than the maximum gain. So we have to be decrease the 3 dB here. Observing the scale 4.78 minus 3 means 1.78. So when it would become 1.78 nearby value, we stop here. Nearly 1.8. Then similarly on the other end also, observe the y2, it would be come to the 1.78 nearly. Okay, 1.78 nearly. So you can see so it would be coming 26.2. This is their FL. You can see here, and FH is nearly coming 1.55 megahertz. Here, this is the value. Okay. In a similar fashion, you can observe the phasor diagram. If you have to see the two scales, first scale is on the minimum value. So as we would be increase the frequency, and when it would be reached to the near the operating frequency, your phase shift is nearly 180. So this is your y2 is representing the phase shift. You can see here your phase shift is 155 nearly. We have to be 175. It would become when x2 value is coming nearly 1k. It would be coming 178 near to the 180 degree. When it would be coming to the 2k, we have applied the operating frequency 2k. So when your value is 2k, you can see your phase shift is 179.3, nearly 180 degree. Not exactly 180, but 180 degree. So in this way, we have observed that the phase shift is nearly 180 degree, and your voltage gain is undistorted voltage gain here. So this is the frequency response curve. You have to see this is the mid-band frequency region where the gain is constant. This is the lower range of the frequency where the voltage gain would be decreases as the frequency decreases. This is the higher frequency range where the voltage gain is again decreases as the frequency is increases. So this would be your upper cutoff frequency, that is nearly 1.5 megahertz, and this is the lower cutoff frequency, that is in the hertz, 26 or 27 hertz. In the similar, this is for bypass capacitor, 100 microfarad and coupling capacitor in 10 microfarad. Similar procedure you can repeat for this by changing the bypass capacitor, because we know that the bypass capacitor is mainly responsible for deciding the value of the lower cutoff frequency. You can change this up to the 22 microfarad. In a similar fashion, this is one of the observation for the frequency response. For the lower cutoff frequency, we have seen that. Now one of the example we have to take for the upper cutoff frequency, and we have to be connect this shunting capacitor 22 nanofarad. So when we have to be connect this, and now we have to be see what is the change would be come to the upper cutoff frequency area. So just do the same procedure. Same is there. Okay, simulate it. Now you can see your curve has little bit changed because we have applied the shunting capacitor. Now you would be see that your value of the voltage gain is nearly same, 4.7 or 4.69. Okay, now decrease by the 3 dB. So 1.69, you have to become back to the 1.69, nearly 1.71. Here also you have to be C 1.69, 1.7. This is the lower cut 3 dB less Y1, Y2 3 dB less. Now observe the lower cutoff frequency is same as in the previous case nearly. It is does not changes because shunting capacitor does not affect on the lower cutoff frequency. But you can see the upper cutoff frequency has significantly decreases. Now it would be decreased from megahertz to the 1.5 megahertz to the 3.2 kilohertz. So this is the main role of the shunting capacitor. It would be affect the upper cutoff frequency. Okay. Like similarly, you can do this frequency response analysis for different value of the capacitance. For bypass, you can change the coupling capacitor value, you can change the bypass capacitor value, you can change the shunting capacitance value, and you can observe the different values are there. Okay. So this is the procedure. Just I want to explain that if you would be going to perform each and every parameter, it would take lots of time. So it is just for your guiding purpose. Now we have to be see some calculated value I have already done. So this is the simulated values for sine wave testing. So this is for coupling capacitor is 10 and bypass is 22. So your FL is 119 hertz and FH is 1.55 megahertz nearly. But when we have to be change the bypass capacitor value from 22 microfarad to the 100 microfarad, you can see the change in the FL. It would be large change in FL because we know that bypass capacitor would be affect the FL only, but the FH would be nearly same in megahertz. But if you have to say the second case, when you have to be change the value of the shunting capacitances, keeping the bypass and coupling capacitor same, but we have to be see here connected the shunting capacitance, your FL would be not changed. It would be similar as the previous case, but FH has been changed because of the shunting. So means shunting capacitor would be responsible for deciding the upper cutoff frequency. Okay. So this is the observations. Now we have to be see the effect on the result table also. So that much parameter we have already discussed. Now in the frequency response for the coupling capacitor 10 microfarad and bypass is 1.54 is your bandwidth megahertz, and CS is 100 microfarad, so your bandwidth is little bit changed, very minutely changed it would be. But when you have to connect without shunt capacitance and with shunt capacity, there are drastic change because basically the bandwidth is mostly depend upon the upper cutoff frequency, not on the lower cutoff frequency very much. So when you connect the shunting capacitance, your upper cutoff frequency has changed significantly. So in this way, you have to be see the value of the output bandwidth is changed from megahertz to the kilohertz. That is the change we have to be actually observe. So if you have to be see, this is all about the this second practical. You can write your conclusion by your own way. Everyone could be write a conclusion in a different way, that because understanding is different. Now in this way, if you have to be see, we have learned the second practice. In this way, we have to be see that we have achieved our outcomes. We have simulated our circuitry for AC analysis, common source amplifier using the modern simulation tool, that is a multi-sim, and we have also analyzed the performance of e-MOSFET amplifier, as well as we have designed the circuit component that would be affecting the frequency response by varying the value of the bypass and shunting capacitor, and we have also seen the how to control the bandwidth of amplifier as per the need of our application. So all both of the objectives we have also completed. You have to be see, we have calculated the Z naught, we have calculated the voltage gain, we have calculated the Zi, and also we have observed the bandwidth. In this way, we have fulfill our all the objectives. So this is in this way we have simulated the is common source amplifier with the help of the multi-sim. Thank you all of you.